Hi, so welcome back to the SACE mathematical methods. So in the previous video, basically we covered the definition of limits and what can you use limits for, which is finding the asymptotes. So we covered how to find horizontal and vertical asymptotes and how to study the behavior around the asymptotes using the idea of limits. So now we proceed to look at the second so-called applications of limits, which is to find the derivatives by the first principle. So let's move on to that. So before we go into that idea, so let's group it into first principle. So before we go into the idea of first principle, essentially, why do we need to define differentiation? Is to generalize the idea of gradient. So if you still remember what you have learned before coming to these mathematical methods, so if let's say you have a straight line y equals to mx plus c, so it doesn't really matter if you measure the gradient at this region or a smaller gradient at the bottom here. So it doesn't matter where you measure the gradient, it always gives you m. Okay, so this is true when your line is I mean basically when your curve is a straight line, but this is not true when, let's say, you have a curve which is not a straight line. For instance, a curve like this. So when you have a curve like this, the gradient over here is definitely greater than the gradient over here. So let's say this is x, this is y, which is why we need to define differentiation. So the main reason is to define, to generalize the idea of gradient for a curve. So now that we know the motivation for differentiation, we will look at some of the equations or some of the functions that you need to study for the differentiation with, especially um, when let's say you, so there's one type of questions whereby you really need to understand how to do it using first principle. So we'll go to that. So let's begin. So let's say you have a curve. So perhaps I put a better line here. So you want to generalize it. So you have this. Sorry. All right. So now let's look at the example closely. So let's say you have this curve. So essentially, the idea of first principle is that you try to define 2 points, or rather, you just try to define 1 point. So let's say this is point X. Perhaps it's better if I write the XY. So essentially, what you're trying to do is to add some small some small number h such that your next point is x plus h and then y prime. So y prime over here is something after. Okay, let us define y to be f of x. So then it is easier for us to define what is y prime, which is just f of x plus h prime. X plus h. So over here you have you added some number h, which is very small by definition. Due to this particular h, your changes in y would be something like f of h. Actually, this is not exactly true because you would assume that your function is linear in terms of x plus h. So I shouldn't write this. So there is some small change. That's what you need to know. So the small change in x, we sometimes also write the delta of x. Small change of y, we sometimes write delta of y. So you can also use these particular symbols. So the whole point here is that you define the gradient and then slowly decrease the value of h in such a way that in the end you reach to the point that you want to find the gradient. Alright? So the gradient is just exactly the same as what you would do when you calculate the gradient for 2 points. So you can write x plus h minus fx. The whole thing you divide by x plus h minus x. So then you would get fx plus h minus fx divided by h. Or this particular gradient, if you use the delta x delta y notation, so it will be delta y divided by delta x. So then the definition of first principle is basically you need to study the limit when h approaches 0, fx plus h minus fx divided by h. So notice that the later part over here is just the definition of gradient, and you try to let that particular small value h to approach 0. So this is a definition of your first principle. So whenever exam question asks you to derive something using the first principle, this is what you need to do. This is the equation that you need to write. So as this particular limit goes to 0, your first principle or your delta y divided by delta x will become dy dx. So this thing will become dy dx. The usual derivation that you know. So now let's look at some examples. So the first example, I will basically show how to derive all the functions that you need to know, but only the polynomial derivation for first principle that you really need to know, because those will be asked in the exams. Alright, so the first one, let's say you have y equals to fx, which is also equals to x squared. So what is the definition of dy dx? It will be when you study the limit of h approaches 0, fx plus h minus fx, and then the whole thing you divide by h. So you just need to plug in equation. So fx plus h will be x plus h, the whole thing square, because your initial function is x squared, minus x squared divided by h. So I will write the equal sign over here. So then the next step that you need to do is to expand it. So you have x squared plus 2hx plus h squared minus x squared divided by h. So your x squared actually gets cancelled off. Sorry, not x, h approaches 0. So you get 2hx plus h squared divided by h. So in the end you have the limit, I don't need the limit of h approaches 0. So over here you can cancel off one h, 2x plus h. So you can just put in h equals to 0 at this point, so you get 2x. That's why differentiating x squared you get 2x. You can try, for instance, y equals to fx equals to x cubed, and so on. You would find this pattern. So if y equals to fx equals to x to the power of n, then the differentiation dy dx will be equals to nx n minus 1. So the index of x move forward to become the coefficients, and then the index minus 1. So that's the first derivation that you need to know. And specifically for this type of equation, you really need to understand how to do the first principle, because this will be asked in the exams. So we will do another 3 cases: the sine and the cos. Sorry, we will do the sine and the cos, and then we will stop here for now, because for tangent essentially there's a better way for us to do it. So I will need to introduce other differentiation rules before I can continue on with the tangent. And then for exponential function, it's possible to derive it using first principle. But logarithm, I also need to introduce another differentiation rules. And that particular differentiation rule is not covered in the SACE syllabus. So for those that are not covered in the SACE syllabus, I would still teach you how to do it, but for that particular cases, I will mark it with the blue colored pen, which you can also see here. So these are blue colored. Essentially, you don't need to know how to prove it, but it's good if you can do it. Alright, so let's continue on. The second case, y equals to fx equals to sine x. So how would you do it? So let's begin. Dy dx. So if you were to do it by the first principle, write down the definition. So this is a definition, and then you plug in all the necessary things that you need to know. So you have sine x plus h minus sine x divided by h. So at this point, you actually need to use one identity, which is the addition of angles. So there is this formula sine a plus b equals to sine A cos B plus sine B cos A. So we are going to use this identity to derive the derivation for sine. Alright, let's continue. So then over here you have limit h approaches 0. So you will have sine A cos h plus sine h cos x. I think it's better for me to move it downwards. And then minus sine x. And the whole thing you divide by h. This is x. So at this point you can introduce another notion, but let's not do that for now. So notice that sine x you can factorize out. There's no h inside. So you have the limit of h approaches 0 cos h minus 1 divided by h. So this is between the first term and the last term. And then I can do that. Let's write the cos x out. And then the limit sine h divided by h. Alright. So here there are two identities that you need to use. Usually if the exam asks you to do that, they will give you those identity. So the first identity is that the limit of h approaches 0, sine h divided by h, this is 0. So that's the first identity. The second identity involves the first part, limit of h approaches 0, cos h minus 1 divided by h. This is 0. Sorry, this is 1. So you need to make use of these two identity to be able to derive the definition, the derivation of sine x by first principle. So then obviously the first term cancel off, becomes 0. So you are left with the second term, which is just cos x. So the third one, y equals to fx equals to cos x. So let's look at the dy dx of this. So always write down the definition, then you won't get things wrong. So now what you have is the limit of h approaches 0, cos x plus h minus cos x, and then the whole thing divided by h. So over here you use another identity, cos a plus b equals to cos a cos b minus sine a sine b. Alright. So then I should have used the blue pen to write all this. Never mind, just make sure that You need to know 1, but not 2 and 3. So then you have cos x cos h minus sine x sine h, and then minus cos x again. Then the whole thing divided by h. So at this point, you know where this is going. Sorry. Essentially, I can factorize out cos x, then write down the limit. You have cos h minus 1 divided by h minus sine x, write down the limit, sine h over h. So previously we said that the limit of cos h minus 1 divided by h is 0. The second one is 1. So therefore you get minus sine x. So I will stop here for now. Tomorrow we will look at chain rule, product rule, quotient rule. Then we go into the tangent of x. And sorry, probably not tomorrow, probably it's next week, because tomorrow's video will be on the A-level past year questions. Alright, thank you.